This is section 14.6, part B. We just looked at the surface integral of scalar functions. We're now going to look at the surface integral of a vector field. In this case, what we're actually going to end up getting is a flux integral. If you imagine what's going on here, hopefully this makes sense. If you imagine that we've got some surface, so let's just say that's a surface S. And then you've got some vector field here. What we're actually going to be calculating is how much of the vector field passes through that surface. So how much of F, this vector field, goes through the surface over a particular portion of that surface, of course. So this will end up being a flux integral. Circulation integral doesn't really make sense here, because a circulation, if you've got a vector field, we can't really push it along a surface. To push something along something, you really need a path. You need a curve, C. So we'll definitely be doing flux integrals when we do our surface integrals of vector fields. All right, so since it's a flux integral, we're thinking F dot n. And oops, that should be D capital S, sorry about that. So little piece of surface area over that surface S. And we'll look at n, and I do want to change this. Instead of saying outward unit normal, we're actually going to make a selection. We'll either be able to do the downward or the upward unit normal. We'll be able to choose that. Okay. It measures the flux of the vector field across that surface in the direction that you choose. It can be evaluated for a vector field F, G and H, on an explicitly defined surface, Z is equal to some function of X and Y, by looking at this. So here's the flux integral. It's the double integral over the surface of the flux, F dot n ds, and we can evaluate it by taking the double integral over R of F dot little n dA. R is still the projection of S onto the xy plane, and little n is just that non-unit normal vector. This I'm going to have to ask you to think way back to chapter 12. The easiest way to find a normal vector for a surface is to use the gradient of that level surface. So if I think about my surface here, Z is equal to Z of X and Y, in order to make it a level surface, remember I have to get it to equal a constant. There are two ways to make that equal to a constant 0, right? I can either do Z minus Z of X and Y equals 0, or I could do Z of X and Y minus Z equals 0. Here, where I keep the Z positive, this one's going to give me the upward normal. And here where I make the Z negative, that's going to give me the downward normal. So either way, if I call this W, then N, the gradient of W, in this case would be the upward normal. And here, N, the gradient of W, will give me the downward normal. So I can just go ahead and pick whichever one I'm interested in for a particular situation. Okay. Again, these formulas are modifiable for surfaces given as x equals or y equals, but for our purposes in this class, we'll just use the ones that are defined in terms of z equals. So in example 3, I would like to find the upward flux for the radial field, F is equal to xyz, across, first of all, the portion of the hyperboloid, z is equal to the square root of 1 plus x squared plus y squared. Below the plane, z equals the square root of 17. So we'll do that part first. All right, so I'm going to give just a quick little sketch here. That's just going to be a hyperboloid of 2 sheets, but we're only looking at the top half, positive square root. Vertex will be at 1. And it'll kind of open like that around the z-axis. And we only go up to the square root of 17 on the z-axis. Now we're actually finding the flux across the hyperboloid, not the plane. So I'm actually not going to shade that in. We're not going to include, that kind of doesn't have a lid on it this time. It's just this surface itself that we're looking for the flux across. And we're looking for the upward flux. So if you can imagine, and I'm going to graph this with us on Maple a little bit later, but if you can imagine the radial field, right, this is the one that comes out from the origin, going this way, what we're looking for is how much of that radial field goes across that hyperboloid, that little cup there, if you will. Because I did ask for the upward flux, and it is going up across, I would expect a positive answer to this particular problem. All right, so let's start putting some pieces together. First of all, let's go ahead and just do R to get that out of the way. If I intersect my z values, of course I can square both sides. And probably I'm going to want to go polar here. So I'm just going to go ahead and call this r squared. So r is 4. And in the xy plane, I would be looking at a circle of radius 4. So there's r. So when I get to the point of setting up my limits of integration, I'll be able to use that. All right, the next thing that I need to do is I need to be able to get my surface defined as a level surface so that I can go ahead and calculate my normal vector. So let's do that next. The surface S, what we actually want the flux across, is this hyperboloid. And since I want the upward flux, I'm going to keep the z positive this time and subtract that over. I'm just going to rewrite it with a fractional exponent here. And this defines that level surface W. It's equal to a constant, so that automatically makes it a level surface. That means that I can now calculate my normal vector n as the gradient of W. And remember, the gradient is the derivative with respect to x, comma, derivative with respect to y, comma, derivative with respect to z. Let me just write that out this time. We haven't talked gradient for a little while. Okay, so let's see. With respect to x, I'm going to get a negative 1/2, 1 plus x squared plus y squared, to the negative 1/2, times 2x, and almost the same thing for y. Just the chain rule gives me a 2y. And then w sub z is a positive 1. You can see again why this makes it the upward normal. I do have a positive z derivative here for my normal vector. Okay, a little bit more here. I'm just going to clean this up a little bit. Let's see. Those 2's will cancel, so I would have a minus x. I'm going to put that over the square root of 1 plus x squared plus y squared. Similarly for the second term. And then the 1. All right, so we're getting there. I have to integrate f dot n, so let's write out f. F was x, y, z. But notice that this is just a double integral, right? A surface integral is a double integral. That means I can only have x's and y's, and therefore I can't use this z. And the way you deal with that is you simply replace the z with the z equation for the surface. On this surface, z is always equal to the square root of 1 plus x squared plus y squared. All right, I think we have everything we need. Looking at all of this stuff, the region is a circle. I'm seeing x squareds plus y squareds everywhere. I think it's likely that this would go really well in polar coordinates. So as I translate this into my integral, I'm going to translate it all into polar. So our flux is the double integral over r of f dot n dA. And let's see, my limits of integration will be 0 to 4 for the r and 0 to 2 pi for the theta. F, let's see, in polar coordinates, actually, you know what? I'm trying to decide here which way I want to go with this. You know what? I'm going to leave this in no, I can't. I already did that. Never mind. We're going to polar. X is our cos theta. Y is our sine theta. And then I have the square root of 1 plus r squared. Dot product with the n, which would be a negative r cos theta over the square root of 1 plus r squared, and then a negative r sine theta over the square root of 1 plus r squared, and then 1. Since I am in polar coordinates, this is going to be r dr d theta. All right, this is a somewhat lengthy problem, so I think I left us a whole blank sheet of paper after here. Let me just flip that around. Okay, here we go. Get set up again here. So I have my double integral. And doing my dot product, this is going to give me a negative r squared cos squared theta over the square root of 1 plus r squared plus, second terms, I would have a negative r squared sine squared theta over the square root of 1 plus r squared plus, here I'm going to have a just square root of 1 plus r squared. And that is all times r dr d theta. All right, let's see if we can be clever here and figure out how to deal with this. I'm thinking that we could combine these two terms since they have a common denominator. And in the numerator, if I factored out a negative r squared, I'd have cos squared plus sine squared, which is just going to be 1. So that's really nice. Just going to get rid of that. That's just 1. And not only was that a nice simplification, but notice that at this point, I no longer have any thetas anywhere in the integrand. So I can use my favorite trick, and I can just pull the 2 pi down, and then I can plug all the rest of that just into the calculator to do the r integral. And when I did that, I got 3.123. Multiplying that by 2 pi gave me 19.623. And that would be my flux then across that bowl-shaped piece of the hyperboloid. Okay, the next part, part B of this problem, asked us to use the same vector field. So F is still x, y, z. And I won't flip back, but you can look if you like. This time, we were looking for the flux across the portion of the cone z is equal to square root of x squared plus y squared. And we only wanted to do this below z equal 2. Right. So that's part B. Let me reset this again. All right, so this time, my surface is a cone. And it's only the part of the cone that's below z equals 2. But again, I only want the flux across the part of the cone, not across that top, so I'm not going to shade that or anything. This is a lidless piece of a cone. And I want to know what the flux of that vector field is across the surface of that cone. So S, my surface, is z equals the square root of x squared plus y squared. And let me go ahead and deal with R here while I'm drawing. To get the region, that circle projected down into the xy plane, once again I would just set my z values equal to get the intersection. So I'd have the square root of x squared plus y squared equals 2. That would be the square root of r squared equals 2, or just r equals 2. And therefore my region R is simply a circle of radius 2. Once again, kind of hinting that I'm probably going to end up in polar coordinates in the long run. But note here that you can never go to polar coordinates until after you've done your derivatives, because the gradient is defined in terms of derivatives with respect to x and y and z. So be sure you don't change this into polar coordinates until after you get that gradient. All right, so we've got our S, and I now need to change that to make that into a level surface. Again, I was looking for the upward flux, so I'm going to keep my z positive. And I'm just going to rewrite that as minus the x squared plus y squared to the 1/2 power equals 0. By setting it equal to a constant, that makes it a level surface, and I'm allowed to use this as the w. And then my normal vector is the gradient of w. Again, w with respect to x, with respect to y, and with respect to z. So in this case, our normal vector is, derivative with respect to x is going to be a negative 1/2 x squared plus y squared to the negative 1/2 times 2x. And very similar for the y derivative. And then the z derivative is just a positive 1. Again, there's that upward normal. Z is positive. Let me simplify that just a little bit. That would give me a minus x over the square root of x squared plus y squared, a minus y over the square root of x squared plus y squared, and a 1. All right, we need to write our vector field F. Again, that was x, y, z, the radial field. But I'm not allowed to use z's in a double integral. So I'll replace z with the z value on this specific surface. I'm only integrating over the surface, so z is always equal to square root of x squared plus y squared on this surface. And then I think I've got everything I need in order to set up my flux integral. So the flux, again, it's the double integral over r of f dot n dA. And looking at all the x squared plus y squareds, as well as the circular region, let's go ahead and convert to polar as we write it down. To get my region, my r will go 0 to 2, and my theta will go 0 to 2 pi. And then I've got f, which is going to be r cosine theta, r sine theta. And notice that that is really the square root of r squared, or just r. Dot product with the normal vector, right here. That'll be a negative r cos theta. And same reasoning, that denominator is just r. And a negative r sine theta. Denominator is just r, comma 1. Polar coordinates, so dA is r, dr, d theta. All right, all set up. We're down to the evaluation piece. So doing my dot product, actually, you know what? Let's go ahead and we can get rid of some r's right off the bat. That's kind of nice. So I'm going to have a negative r cos squared theta and then a negative r sine squared theta and then a plus r. R dr d theta. And again in here, I can go ahead and factor out a negative r, which makes that cos squared theta plus sine squared theta. Then I've got that plus r, r dr d theta. But that's just 1. So in fact, what I have inside my brackets is really minus r plus r, which is going to give me a factor of 0 here. And of course, 0 times anything is still 0. So I end up getting a final answer of 0 for my flux here. All right, so there's the calculations of the two fluxes. Before we call ourselves completely done with this section, I'd like us to take a quick look at what's going on by looking at the graphs of these in Maple. All right, here you can see I've just done a with plots, and then I've done the implicit plot 3D, and this is that hyperboloid. Z was the square root of 1 plus x squared plus y squared. And here you go. It is graphed in Maple. I've done a couple of things just to regulate the transparency and the color so we can see a little bit better later on. I've just assigned that the name A so I can later display it along with the vector field. I then did a with vector calculus, and here's my three-dimensional field plot, and there's that radial vector field, x, y, z. I called that B, right? I assigned it as a B colon equals here. And then I displayed both in the same graph. So there's display A and B, and you can see the hyperboloid, the green hyperboloid with the red vector field kind of coming through it. If I tilt this a little bit, and I'm actually going to try and look straight down on it. So I'm going to try and line this up so I can look straight down the z-axis. There we go. Okay. What I want you to specifically notice is that there are vectors that pass through the boundary of that hyperboloid. You can see one right here, for example, right? The little vector for the vector field starts inside the hyperboloid and it ends outside. So there's that flux that's happening. what's crossing the boundary, the part of the vector field that's crossing the boundary of the hyperboloid. All right, now let's look at the cone. Here's my plot for my cone, the square root of x squared plus y squared. And you can see the cone right here. And I then displayed the cone with the same radial vector field right here. If I tilt this one and look straight down on top of it, as though I'm looking right down the z-axis again, what I'd like you to notice this time is that the vector field never crosses the boundary of the cone. If a vector starts inside the cone, it ends either within the cone or at the edge of the cone. It doesn't actually cross the boundary of the cone. So the vectors either start inside and stay inside, or start outside and stay outside. They don't cross the boundary. And that's why the flux was 0 for this radial vector field across the cone. None of the vectors cross the boundary of that surface. All right, that brings us to the end of section 14.6.